let's begin. My talk is basically going to be on this work that we did, that we have on archive preprint a couple of weeks ago. Now we are trying to ready it up for a journal submission. It's on perturbative Kähler Moduli inflation. Before I get into the meat and potatoes of the paper, because I want to keep it relatively friendly, and this talk is a relatively friendly one, it's not completely formal. I wanted to sort of coax the necessity of inflation, string inflation, and like the caveats and like the benefits of our model per se, basically. So first off, everybody and their mother knows the Big Bang Theory, right? The universe is expanding. Is it showing? Yeah. The universe is expanding, it's ever expanding at an highly accelerating rate, right? Which is, it's a daunting result, and it's effectively explained by the FLRW metric that we see. Why doesn't this? Okay. This FLRW metric that we see here, where this encodes the information of the acceleration rate of sorts, or the rate at which the universe expands of sorts. Okay. So initially, the universe was basically like a hot bowl of soup, effectively at around 10 to the power 32 Kelvin. And then it evolved and expanded to what we see now at like TCMB, which is 2.73 Kelvin, which is the average temperature of our universe. Okay. Now, the Big Bang model was a pretty good model. It explained like the existence and properties of the cosmic microwave background after the region of last scattering, and it also explains the particles that we experience today. We are all stardust. We're all products of Big Bang nucleosynthesis, right? All of these are pretty accurately explained by the Big Bang model. However, it doesn't. There comes a problem when we try to look at the very near initial dynamics of our universe, right? There seems to be a requirement where our universe underwent a exponentially rapid de Sitter-like expansion. If you don't account for this type of very distinct expansion, then you don't really reconcile the kinds of problems that we face if we're just considering an normally ever expanding universe. So, this is just a diagram. Like, it basically shows off the universe from the beginning to today. And as you can see, that de Sitter-like expansion epoch of the universe is the best explanation that we have thus far is inflation. And inflation is just this small part here, and then of course we have basically the rest of the dynamics of the evolving universe. It just so happens to be that this small patch of the universe, I think if I'm not mistaken, from 10 to the power minus 34 seconds to 10 to the power minus 32 seconds, we face a lot of problems in trying to probe the dynamics of it. And it's been 40 years, we still don't have a proper good model for this kind of thing. So you understand the gravity of it all. And it, at the end of the day, is the gravity of it all. Because gravity is the leading force that decouples at this point and is the driving, is the kind of mediator of sorts in this kind of epoch. Moving on. So yeah, how Big Bang fails to explain what we know, the key CMB observations which were done. Basically, there were 3 experiments. I think there's another 4th one which was done in 2025. Don't quote me. I think there was 1996 by Kobe, WMAP at 2003, and Planck at 2020. They effectively told all of them with varying accuracies, with ever increasing accuracies, the same story. The fact that whenever 2 different observers look at the night sky, they find a level of isotropy in the CMB temperature that shouldn't be really, because it breaks a level of causality. It means that the universe underwent a certain kind of dynamics that required there to be some causality, for which we receive such levels of isotropies in the detected CMB temperature, which is 2.73. Wherever you look, you're going to find that the temperature of the universe is going to be 2.73 Kelvin. Okay, and that breaks the kind of understanding that we have if we just consider like a normal Big Bang kind of model. There has to be some kind of reconciliation in between. And as I said so before, we think that's inflation. So there are also other aspects of it as well. There are isotropies. The isotropy is the fact that it's 2.73 kelvins, but there are also peaks that are certain anisotropies noticed when you're looking at the night sky and you try to detect like the temperature kind of spikes, basically. Those anisotropies are also kind of not effectively explainable with a normal Big Bang model. And it's the fact that the universe is basically almost flat, right? The universe, now we know it's quite literally flat. We can't account for that. It's not fat, it's flat. Now, again, as I mentioned before, inflation has this kind of a expansion rate where it goes like this, exponential of h lambda t, where h lambda is effectively a dot by a, okay? And a is the scale factor. So we now have to explain that epoch, right? And to explain, we use whatever tools we have at hand, the Lagrangian. Any dynamics that you can have, that you want to pick and probe, you must make a Lagrangian. Physicists basically postulated that let's do this by utilizing effectively a scalar. Now, if I'm not mistaken, you can also do it with fermions, like basically with like using Dirac theory. But things get a lot more complicated. With scalars, things are still easy, and they are effective enough to explain the situation as it is. Yeah. So we have a scalar that we called that is driving effectively this period where the universe underwent this type of expansion rate. Okay, and that theory, that kind of dynamics, is driven by this scalar field called an inflaton. Now, this is the image basically of the night sky, and as you can see, there's a level of nice distribution of all of these like blue spots, effectively explaining those isotropic 2.73 kelvins, and those specific red spots are things that we have to kind of find a way to explain as well. Moving forward, we only have gravity, right? We have gravity at our disposal in this kind of regime. All the other forces have not yet separated out and do not their dynamics are kind of, you can ignore them, or they're not really available at that point. At such high energy scales, only gravity has such a highly energetic coupling constant, so it'll take over. When you're doing standard model, for example, the effective background energy isn't strong enough, and you can effectively ignore gravity, which is why when you're doing standard model, you do SU3 cross SU2 cross U1, you effectively forget gravity, because gravity's highly energetic behavior is only pretty evident at very, very highly energetic scales, and such energetic scales, they'll take over. Okay, so we have our action at place, and of course this is the very generic action that you can provide given a scalar field theory in non-trivial background. Here you have the Ricci scalar. Here you have the kinetic term that drives this inflaton. Inflaton is, again, the scalar field that drives inflation. And then a very important potential. Because inflation not only has to occur, but it has to occur for a certain period of time, right? To match our understanding of CMB isotropies and flatness and everything, it has to occur for a certain period of time. So you must have a kind of potential that holds that dynamics for that period of time. That means that the potential for most of the dynamics is going to be much, as in d nu phi, half g mu nu, must be much less than v of phi. You must require that if you're going to allow the universe a certain amount of expansion time so that it can effectively evolve and give us inflation and the necessary tools to get how we see our universe as today, right? And we solve the equation of motion varying the field phi, and you get this basic term. And the flat potential that is required, as you can see, this is the potential. Okay, the pointer is a little... This is our potential. And as you can see, this is our regime. It's slowly rolling. That's why we oftentimes call it as like the slow roll potential. That's the effective potential that is required to kind of drive inflationary dynamics. Okay, this is this region where inflation occurs. All right, now that we have a region of time where we consider inflation to take place, we must then derive a couple of consistency conditions, right? Given the fact that how we kind of want our dynamics to be. And from basically the equation of motion, you can derive these two very important parameters. These are called, these are like the slow roll parameters, okay? And it's very important that if you want to sustain a certain period of time where inflation correctly takes place to explain today, you must have an epsilon and eta which is much, much less than 1, all right? So these are the forms, these are derived, these are derived pretty easily from the equation of motion. And these are the, of course, slow roll parameters. And then we also have like scalar inflaton perturbations. These fields also undergo perturbations, basically. And these perturbations also are pretty important as well. These scalar, the theory of inflation, inflationary perturbation, it kind of leads to like basically required levels that we need, an NS of 0.9743, which is also kind of detected as well. This is, I think, the latest data that I have at hand. And a further observable posited by inflation is the scalar to tensor ratio, okay? And from experiments, we needed to be around we needed to have our R, which is the scalar to tensor ratio, to be like less than 0.032, okay? So as we can see, inflation really provides us, this kind of like dynamics really provides us with a lot of values. And these values are gonna come in handy if we're gonna try to get a good model going. Because you can make many kinds of potentials that fit the bill, but they have to also fit these kinds of predictions. So it's quite a inflationary cosmology is quite a very uniquely different kind of physics endeavor of sorts. Okay, so, okay. Observables from inflation. So this scalar to tensor ratio that I mentioned, a measurable amount of a scalar to tensor ratio, which would predict, like, detect primordial gravitational waves. It's gravitational waves from beyond back, basically. And the scalar fluctuations actually produce the necessary CMB anisotropies that we're talking about, and lay the seed for the large-scale structures that we see today, basically. So there's a lot that's going on in that small period of time. It sets the kind of background for a lot of things to come way, as we see now. So there's also this thing that we calculate, which is called the number of e-folds, which is dependent, which effectively looks like this, and it can also be rewritten to be effectively dependent on the potential. And we require a number of exponential e-folding to be around 50 to 60. That's the amount of e-folds that you require for sustained inflation, okay? And of course, the analysis of CMB tensor fluctuations, it would imply the fact that there's an upper bound on inflationary dynamics, which is about 10 to the power 16 GeV, which is a very, very high, which is a very high energy scale. This kind of high energy scale would kind of give you the kind of idea that, okay, there needs to be some kind of UV control that is required to effectively understand the kind of dynamics that takes place. But who knows, maybe we can try and use effective field theory techniques that we use that we've been successful thus far in standard model, and maybe we could get away with it. Unfortunately, that doesn't hold true here. Before I go into like string theory and the necessity of string theory, I just want to take like 5 minutes to try and motivate what is effective field theory and why effective field theory kind of breaks down. So Effective field theory, the general key idea is like there are different kinds of physics phenomena at play at different kind of energy scales. Okay, like take for example the electron interactions, right? At the most basic of scales, we know from very young age the Coulomb interaction, right? If you think about it from a momentum space point of view, it goes as 1 upon q square, or like 1 upon r square in like, which is the inverse square law, and you Fourier transform it, and then you can think of it from the momentum point of view as 1 upon q square, right? That's the Coulombic interaction. However, at higher energies, we find that these kinds of simplistic viewpoints don't really hold true. You must figure out another way to gauge these kinds of interactions to get the seed of, to basically make hay and understand, which was Lamb shift in the 1920s. Lamb shift had values which were not in concordance to the kind of ways in which quantum mechanics was done for the hydrogen atom. So they had to figure out a way, and thank God for Feynman, we were able to renormalize quantum electrodynamics, and we were able to effectively explain a kind of log shift from the inverted square law. So you can see at this lower energy scales, these kinds of scale shifts don't really occur because, and they're not going to. Those kinds of physics are only privy once you probe a certain energy in which they become inherently privy, basically at higher energy scales. And so a similar, so with that kind of like underlying theology at hand, what we do effectively is an effective field theory whenever we do any kind of standard model. Because in the case of standard model, whenever you're doing any kind of quantum field theory is a hilariously non-renormalizable theory, right? All we have are perturbative techniques, tacking on loop diagrams, that to loop diagrams. Let's say you have an interaction. These kinds of diagrams are at place. And these kinds of diagrams, without any considerations of loops, you're going to just get your 1 upon q square, which is in the case of electrodynamic or like Coulomb interaction, 1 upon q square, inverse square law. You start tacking on from perturbation theories these kinds of loops, and then you start noticing differences. You start noticing additive changes to these kinds of interactions, right? Okay, so the point is, you can theoretically tack on as many loops as you want, right? As many loops as you want, as many perturbative techniques as you want, but you're not going to be able to, at the very end, be able to solve the integral. The integral is highly non-trivial, and they have too many divergences. And so basically then we have an effective field theory technique, which is like, okay, fine, we have these divergences, but for the time being, you don't consider at such higher energy levels. What you do is effectively integrate out all these higher energy modes, keep the lighter energy modes that are effectively regularizable and then further renormalizable, and then you have an effective field theory with which you can work on, right? Which is relatively, yeah, the key word here is relatively easy when you're considering like simple standard model interaction. With gravitational interactions have a tricky problem in which its coupling constant is effectively 1 upon m Planck squared in any kind of loop diagrams. 1 upon m Planck squared is highly energetic, right? It's very high energies. You cannot effectively integrate it out. If you want to tack on to understand new physics at the end of the day, you're not able to even at a one loop diagram point of view. So at the end of the day, you're just getting normal GR, which is, you're not really quantizing anything at that point. So gravity is a problem. What about inflation? Good enough. Dealing with scalar fields is renormalizable at like relative higher orders. The coupling constants aren't a problem. The problem becomes the fact that take the action, right? The action is supposed to be like this, d4x, and some ingredients here. Now the action is supposed to give you a real number, right? So if this has to effectively cancel out the dimensions of whatever you have inside, right? And that's why we oftentimes deal with what are known as like 5-4 theories. The problem comes in inflation is when you're trying to calculate these slow roll parameters, especially this form eta. Now, if you remember, eta is required to be much, much less than 1. But since eta inherently is the double derivative of the potential, what you find is 5 to the power 6 kinds of fields are privy now to the sensitivities of the dynamics of your model. 5 to the power 6 is not it's not renormalizable. You cannot do that. Unfortunately, then such UV models, such UV parts of your total Lagrangian, which you could have if you're using sensible effective field theory techniques that you could have ignored, you cannot ignore anymore. You're going to get an eta parameter that is of order 1, which cannot occur and give you a proper region in which inflation can take place. So it's an uninsurable disparity which we cannot ignore. And again, to reiterate, the energy scale is at 10 to the power 16 GeV. So really, we need a better framework to work with. Simple quantum field theory, no, by simple I mean relatively simple. Simple quantum field theory is not, and effective field theory techniques are not strong enough, right? We need to then figure out a better framework which is inherently UV complete at all kinds of expansions, at all perturbative levels, such that we are not then dispelled by the problems that we have in these kinds of models and these eta problems, basically. So here comes string theory, right? Now, are a lot of you people understand the generic, just string theory as a general theory? As general, of course, you don't have to be experts at it. Hands up, please. Really? Okay. I know you guys know a little bit. All right. Anywho, the very simplistic take on string theory is any kind of physics and any kind of dynamics that you do in any particle interactions or anything in it. Whatever you're doing, it's the dynamics of point particles. Okay. Point particles are effectively zero-dimensional objects, right? So the understanding in the 70s, what had happened was QED was effectively nicely renormalized, gave good results. Weak interactions got finally renormalized by dimensional regularization, gave good results, pretty accurate. Quantum chromodynamics, as in strong interactions, was not giving us favorable results. Strong interactions require further nuances for it to work as a quantum field theory. So there was an understanding that there was an idea that maybe strong interactions might not be a quantum field theory. Let's try to work with this new kind of device that we've kind of made, which is a string theory. It's a one-dimensional object, which is why it's given the name string. It's effectively, the Lagrangian is of a one-dimensional relativistic string, and then you basically work with it. It found good conjunctions with hadronic collisions, but it was mired by other problems as well. It was effectively trying to fill up a pond with a bucket. It's quite a difficult task. But one man's waste is another man's gold. Okay? What happened was, when trying to quantize strings, it effectively pops out particles of characteristics of spin 2. Now, if you know anything about spin 0 are scalar fields, spin half are fermions, any kind of odd integer particles are fermions, and spin half, spin 3 halves, even though spin 3 half Lagrangians are not really, other than supersymmetric extensions, spin 3 half Lagrangians cannot be, there are a lot of problems with that. Spin half, spin 1 is effectively all the gauge particles, and then spin 2, which is the gauge particle of gravity, right? Graviton, right? It was a very famous work done by Steven Weinberg in the 80s, if I'm not wrong, who calculated using a similar QED techniques that if graviton was indeed a gauge particle of gravity, it had to be spin 2. And string theory, once you quantize it, it effectively gives out all of these fields and a spin 2 particle, even though you don't require it. Which means the fact that this framework, this string theory framework, is UV compliant. You are safe in the kind of regime that you're dealing with. Okay? So string theory is a UV complete theory. Any kind of effective field theory that you try to derive from string theory is not going to be mired by the same problems that you would have if you go from quantum field theory to an effective field theory, right? And so you effectively try to build phenomenological tools that would give rise to the required effective field theory. And so we have string theory, which maybe you guys know, famously, it's always like thrown around. Oh my God, 26 dimensions is the required dimensions for a consistent string theory. Now, I know it's a very, like, it's a large pill to swallow, but to me, I guess maybe I'm jaded. It's not a large pill to swallow. To me, it's something like, yeah, space-time is, as posited by Einstein, space-time is quite dynamical, right? Why not dimensions be dynamical as well? And people oftentimes think of these extra dimensions as these over-encompassing, non-compact dimensions, but it's not the same little old brother Minkowski that it is. It's a very different kind of understanding of these extra dimensions. Effectively, you want, at the end of the day, you want all of these theories to condense and give us at certain limits. Let's say gravity, right? In Einstein's theory of gravity, once you take the non-relativistic limit, you take the weak field approximation, you effectively end up with Newton's gravity, as in the 1/r² law. Yeah? And so in the same way, we need to have that these kinds of theories give these inverse square laws. So these dimensions inherently cannot be non-compact. These are compact dimensions that fold over, and these non-compact dimensions effectively give rise to additive effects that one would not feel at lower energies. It's only at higher energies where we are privy to these kinds of higher dimensions. So yes, bosonic string theory, the effectively open string, like the quantization of it requires the fact that we have 26 dimensions. Now we have the caveat of yes, exactly. Yes. So string theory, we have the advent of supersymmetry, right? Supersymmetry is effectively grand algebraic like modulation in trying to incorporate a very easy correspondence between fermions and like bosons of sorts. And in incorporating supersymmetry to these bosonic field theories, we give rise to something called superstring theory. And we have, for different kinds of supersymmetries used for and to incorporate different things, we have 5 different types of superstring theories themselves. But fret not, there are very strong dualities, even though there are many people who are trying to hack at the dualities themselves. We have very strong dualities that effectively make all of these 5 superstring theories relate to each other. There are very strong dualities at play here. So what we're going to work with is the type 2b superstring theory. Okay, type 2b is a very type 2b. It's easy to play around with type 2b phenomenology. That's why we use it. And with duality at play here, we can basically say that all the others would hold true as well for these kinds of things. And yeah, with superstring theory, we can incorporate fermions because the 26-dimensional case was just a bosonic string theory. Because of the advent of supersymmetry, we can incorporate fermions because at the end of the day, if not for fermions, we wouldn't exist ourselves. And for type 2b consistency reasons, we require our dimensions to be equal to 10. And you might wonder what the kind of line element would look like. I'll try to give it as best as possible. Let's say we have our ds square is equals to the traditional g mu nu dx mu dx nu. This is, of course, our Minkowski part. Mu and nu run from 0 to effectively 4, right? And then we have this extension, gmn dym dyn, right? And we have these m's and n's similarly run from 4 to 9, and thus incorporating basically 10 effective dimensions. Now this is, of course, it's Minkowski, non-compact. If it wasn't non-compact, we wouldn't be able to explain our universe. This, we require it to be compact, okay? This is a very special, this is encompassed by a very special kind of manifold called the Calabi-Yau manifold. It's, yes?
Why is it necessary for that part to be
That part to be, this part? This is our universe, right? It's like four-dimensional. We need it to be Minkowski, right? That's my point. You can have it, you can play around with this model, you can have it be anything you want, but purely from a pheno point of view, let's have it be Minkowski, basically. So now we have this Calabi-Yau. Calabi-Yau for a lot of computational simplicities, which are, of course, logical as well. It's Ricci flat. It is first Chern class goes to 0 and yada yada. Yes?
So there is no gravity in this curve?
There's nothing here. For the time being, I haven't spoken anything about gravity. But
The gravity comes into the theory by the G event first?
yes, basically. Effectively from that. Here, there's nothing. All the encompassing, that encompasses, and basically at whatever limit that you, the limit that you want to take, you'll get your inverse square law or you'll get your GR, basically. You wanted this to be folding over. Okay, I want to motivate these extra dimensions now, right? I've said a lot of things, but I haven't motivated it. I've said that let's just accept the fact that we have higher dimensions, but let's consider this very famous example posited by Kaluza and Klein in 1926, a long time ago. So it tries to effectively, there's also a gravitational counterpart to it, but I'm only going to show you the example of the scalar field, effectively. So we have a 5-dimensional scalar field in this space-time, and we have this S1, right? This S1 is compact. And then we have this normal M4. So the fact that we have this compact periodic S1, it allows us to write our 5-dimensional phi, our scalar field, in this manner where it breaks up into this phi n, which depends on the 4 space-time dimensions, which belong to M4, and then you have this periodic exponential part. And what happens, remember, sorry, don't remember, I forgot to even mention this. This is a massless scalar field. Right? Pure kinetic terms, this is just mass. Of course, the mass term would be determined by the potential that you would tack onto it, right? It would come from the double derivative of the potential with respect to phi. That would be your mass matrix. But here, let's start with a massless scalar field and let's see what happens. Now, we of course have the very famous box equation, d mu phi, if you consider it to be equal to 0, which is going to be the general equation of motion for a Klein-Gordon equation. What you find is these additive term. Effectively, your mass square is your mass term is being contributed by this extra manifold that you considered, extra kind of space-time that you considered S1, where it is compact. So these extra dimensions, these compact extra dimensions, once you try to incorporate it into your normal theory, once you try to go from 5D to 4D, you will see that these have certain effects on your 4-dimensional dynamics as well, okay? So, yeah, so for m squared is equals to n squared by r squared, and for n non-equal to 0, for n is equals to 0, you just get your massless, you just get the massless Klein-Gordon equation of motion. But for n non-equal to 0, you effectively get an infinite tower of massive states, okay? N can be 1 to basically infinity, as you can see from this decomposition. All right, moving on. We have, let's work with our phenomenological construction to get our inflation in the first place. And I'll just give you a couple of keywords that are going to be important in the coming slides. We have moduli fields that are effectively scalar fields that inscribe information regarding these higher dimensions, okay? And there's a requirement of moduli stabilization, we need these moduli to be effectively at some kind of minima to have effective 10 to 4D, effectively going from 10 dimensions to 4 dimensions. And a very important work, and from metric deformations of the Calabi-Yau, you get to, for the Kähler potential, these kinds of these 3 effective terms, right? And a seminal work done by Giddings, Kachru, and Pulczynski back in 2002, they introduced fluxes, and what they did was they stabilized these 2 terms. They kind of stabilized it to a VEV, to a vacuum expectation value, so you kind of do not have to like incorporate other kinds of effects to it to stabilize it. For the time being, any kind of phenomenological constructions, you don't have to concentrate on these parts effectively. So what we're left with is this part to play with. And of course, by the works of Gukov, Waffa, Witten, we have this effective form of the superpotential, and we can also play around with the superpotential. According to supersymmetry, these are the 2 tools that you need to construct an effective Lagrangian, right? A superpotential and a Kähler potential. To do so, we have the n is equals to 1 supergravity construction via type 2b. Now, type 2b is not necessarily n is equals to 1, it's n is equals to 2. But n is equals to 1 is a far more workable framework to work with. So after you need to really further tackle on something called an orientifold projections, which effectively takes you from n is equals to 2 to n is equals to 1 supersymmetry. At n is equals to 1 supersymmetry, supergravity, we have this scalar potential form. You see this potential, this effective potential, this what we call is the F-term potential. It effectively takes in all the Kähler, it takes in as ingredients the Kähler potential and the superpotential to spit out an effective potential that you can kind of work with. And as I said so before, in inflation, potential is the name of the game, right? You need a very good potential to work and give you those necessary required 50 to 60 e-folds and and also the other parameter represent respecting values, right? So this is going to be our the whole pursuit is the pursuit to get an effective potential here, right? Any kind of tools that you use, you're really trying to get a nice potential. So in four-dimensional effective supergravity, you can incorporate fluxes, non-perturbative effects, perturbative effects, effectively alpha prime corrections, alpha prime cube corrections, string loop corrections, and incorporate objects like branes and whatnot to get what you want. Those are the tools that are going to feed into your Kähler potential and superpotential effectively. Now, I'm going to go through this pretty fast. Not fast. I'll go through this as best as I can. It's basically, historically, moduli, as I mentioned before, moduli stabilization is pretty necessary for it to have like a proper EFT. Okay. Now, there are 2 main contending moduli stabilization techniques. One posited by Kachru et al. In 2003, known as the KKLT, and the other by Balasubramaniam and Quevedo in 2005, known as the LVS, which is the large volume scenario. Okay, so both of these models have things in common, of course, but it's the tiny little details where they differ. Both of these have superpotentials where this doubly knot is set, and you have these kinds of non-perturbative effects tacked on. Okay, both of them have these non-perturbative effects tacked on, and these non-perturbative effects are quite useful, are quite necessary when you try to stabilize the moduli. You have the for KKLT, they utilize a very relatively comparatively simplistic single modulus case where the volume, because these extra dimensions fold over and effectively give you a kind of volume, right? This is a compact kind of space. It's going to fold in and give you a kind of volume. So think about it like that. KKLT requires a single modulus to use it, the most simplest form of KKLT. Both of these models have further kind of additions to it, but I'm only presenting the most simplest form of these 2. This is the single modulus case. For LVS, you can incorporate multiple moduli. In this case, there's the addition of one other modulus. Okay. For the Kähler potential, it just with all the others, a la Giddings, Kachru, and Pulczynski, with all the other parts of the Kähler potential stabilized, you only have the term that's dependent on the volume itself. With LVS, we also start incorporating alpha prime corrections. Okay, alpha prime corrections are incorporated here, and thus it changes the dynamics a little bit. Too important, basically. So superpotentials I spoke about. The stabilization technique effectively for the KKLT is very simply just the added non-perturbative effects that you tacked onto the superpotential. In LVS, both the additions to the Kähler potential, which are the alpha prime corrections, and the non-perturbative effects of the superpotential are necessary to reach stabilization techniques. What you get in trying to use a kind of Swiss cheese volume type, because this is called the Swiss cheese, very famously. Why Swiss cheese and not any other type of cheese? Basically, this is known as what is called the blow-up moduli. It kind of can be collapsed into type of a singularity. So imagine a Swiss cheese. The Swiss cheese has a lot of holes in it, right? So those tau s, if tau b, this tau b represents the entirety of the cheese, these tau s's represent those small little holes that can be eventually collapsed into a singularity. Okay, these tau s's are the driving forces of what you'll see in Kähler Moduli inflation, and in this case for vacuum construction, effectively. So what we're trying to do again is trying to stabilize the moduli and get the de Sitter vacuum that we see today. Can we construct a de Sitter vacuum that we see today with a very the de Sitter vacuum that we have with a very highly negligible but still non-zero cosmological constant of the universe today? You compute from these using effectively this potential form. You compute an ADS vacuum potential. Now it's ADS. ADS is not our universe, right? Our universe is de Sitter at near vacuum. Our universe is de Sitter. So what you need effectively a prescription to go from ADS to DS. And the prescription are many aplenty. There are many ways to get these kinds of uplifting of sorts. You're going to go from a negative potential effectively to a positive one. So that requires an uplifting. It's like a small energy you're providing with whatever kind of objects you can. There are many kinds of, like, you can add like D-branes and everything to get this kind of, get the required de Sitter effectively. And so yeah, you can get a de Sitter kind of vacuum solution with both of these kinds of models. What happens is LVS, which I'm partially privy to, LVS has doubly naught values of order 1, whereas KKLT has doubly naught values of high, like very, very low doubly naught values. So there's always been complaint against KKLT, the fact that, like, okay, can you really effectively find out Calabi-Yaus? Because again, Calabi-Yau, the compact dimensions, the extra 6 dimensions that you require, it's not really something that is really known to us. It's kind of, it's like a needle in a haystack kind of a manifold, and we're trying to figure it out what effectively is the manifold that defines our requirements. So a huge complaint was, in the case of KKLT, was with such low W naught values, is such low superpotential, like Gukov-Witten superpotential term, can you effectively find out a good amount of Calabi-Yaus this way? But apparently they were successful, but we'll see how we proceed forward. Anywho, I present before hours this work by Conlon and Quevedo, the Kähler Moduli inflation. Effectively, you have the same type of like Swiss cheese volume form, which is this. And of course, there should be another tau phi, 3/2, right? This is the moduli stabilization blow-up cycle, and this is the blow-up cycle that's your leading inflaton candidate, right? Because for those of you who have done some kind of cosmology course, you know, if you know the Starobinsky type potential, Starobinsky type potentials that are the potentials that are basically the driving force of inflation are of these types. Some exponential with minus, there's something here, right? And with these kinds of volume forms, and with non-perturbative techniques here, what you will find is a potential that has these minus tau phi terms. Looks eerily similar to a Starobinsky type model, which gives us the kind of motivation to move forward. Okay, given such a friendly exchange, we can try to motivate inflation from string theory. Okay, so the Kähler Moduli inflation, same beans and potatoes as the LVS moduli stabilization technique. Effectively, there's just another blow-up cycle, which is the inflaton candidate. You use, again, this potential form, this V of F, to compute basically your effective potential. And if you displace the phi potential away from the minimum, which is explained by tau s, if you put this is your basically this term. Okay, this is how you make a correspondence between these two kinds of potentials, right? And now, I just wanted to show this photo. I'll show this photo later. You keep the overall volume fixed because this scenario is called a large volume scenario. The tau b, which it governs the whole bulk of the volume, is you keep the overall volume basically stabilized. The stabilization technique is, of course, driven by tau s, and then you get an exponentially flat potential that enables your required slow roll dynamics. And with that, we find a canonically normalized potential form with respect to phi, scalar field R requires scalar field phi, and we get such values for n and r. This is a pretty good result. However, this model is mired by the fact that it does not give rise to values of primordial density fluctuations, which would give us detectable gravitational waves. So this is kind of a very big negative aspect of this model. But there were further contributions. Further work has been done, most recently by Bansal et al. In 2024, who added string loop corrections to the Kähler potential and found that they could circumnavigate around the problem, basically, adding to better phenomenological results. So what this diagram basically entails, as you can see, this is the stabilized volume cycle, right? It's the overall volume, which can be the overall volume almost basically is tau b, and then you have these blow-up cycles basically. Tau s being the mode that drives the stabilization, and tau phi being the inflationary blow-up cycle. Okay, so yeah. Now let's move to ours. Enough of talking about other people's work. Let's now talk about my work, and unfortunately I think I have 10 or 15 more minutes left. Okay, sorry about that. So our work basically builds off of effectively now 20 years of trying to achieve inflation from string theory. So yeah, a lot of work has been done. We still don't know what to do. So our model uses a similar Swiss cheese type of volume form with same blow-up modulus, which effectively drives moduli stabilization. However, the caveat of our model is our superpotential is kept bare. It's tree superpotential. If you remember, superpotentials in the previous the stabilization techniques and the previous Kähler Moduli inflation had W is equals to W naught plus A phi, AS e to the power minus tau s AS and plus A phi e to the power minus A phi tau phi, right? You had these requirements, okay? These are highly non-trivial requirements to have in your superpotential, and you can make arguments for these, but of course, keeping the superpotential bare makes the argument for your model that your model is far more natural in off sorts. So our model basically dispels with that. We don't have any non-perturbative effects on our superpotential. We keep our superpotential bare at W naught, say a stabilized superpotential. What we have is tacked on stuff inside our Kähler potential, and I will go through what we figured out with why we tacked on a lot of things with our Kähler potential of sorts. We tacked on to Kähler potential where K naught looks like this. You have the this is effectively the expanded like Swiss cheese form of V, and what we have is further moduli redefinitions. Effectively, let's say tau B, there's a redefinition that is occurring at each moduli level. Basically, tau B goes as tau B minus alpha ln V, and V, since you can approximate it to be around tau B 3/2, because tau B is much larger than all of these blow up moduli, we effectively kept it as alpha ln tau B, because otherwise we weren't able to compute stuff if you don't make these considerations. So, and of course, the blow up cycle tau S also receives modular redefinitions. It goes as tau S. Our notation is a little different here, plus beta ln V. Okay, these are slight redefinitions from the general modulus. Okay, and then yeah, we have log loop terms and the dilaton and everything, and tacked on to the Kähler potential, this is K naught, and then we have further corrections that we get from K loop. Effectively, these are string loop corrections, expansion in GS, right? String theory has parameters alpha, prime, and GS. So GS prime expansions, you may think of it, these are like genus expansions. Effectively, string theory interactions in string theory occur at like world sheets, right? If you think of zero-dimensional objects, if their interactions occur at world lines, string theoretic interactions occur effectively at world sheets. They span a two-dimensional kind of space when they're interacting. Once you try to do that, you're kind of involved topology in another. So these kinds of genus expansions exist where such non-trivial loop. You can think of these genus expansions as in quantum field theory where you have loop expansions, okay? So you incorporate loop expansions. These kinds of similar loop expansions were the ones that were also used by Bonsall when effectively they modified the blow-up inflation. Their paper is called the loop blow-up inflation. Their leading candidate for inflation are the loops, and yeah, we also incorporated loops, and we found two different cases. And one of our case actually, our final effective field theory, our effective potential corresponds to the potential that they calculated as well. Okay, superpotential, as I said so before, is W naught, and the effective potential using again the potential, the expression for potential that you have, which take in derivatives of the superpotential and the Kähler potential. You get like this effective potential. As you can see, this is of course the minimum, and you need the inflation to be highly displaced from the minimum. And as you can see, we have two different classes. One goes as tau s to the power half, and one goes as tau s to the power minus half. Okay, so we effectively have two different kinds of potentials to play with. Now it's up to observations and other people's scrutiny which class of model effectively takes place, right? Because we're dealing with a range of values. We're not really dealing with effectively a specific set of values of sorts. So after canonically normalizing, after you take tau s is equals to this form of phi, you get your potential to be in terms of your scalar field phi, your effective potential. And this is, of course, the first case, which is from this. And this is our second case, which is from this, right? And also these prefactors, we baked it into V naught, which are not taken up over already by the canonical normalization, okay? This second case highly correlates with loop blow-up inflation. Okay, this highly corroborates with loop blow-up inflation. And since it highly corroborates with loop blow-up inflation, we had some kind of confidence with our model, effectively, of sorts. And a very important part of our model is the fact that these moduli redefinitions in the first place. These moduli, as I mentioned before, in any type of like LVS or KKLT, those kinds of vacuum constructions, or when you're trying to do like any kind of inflation or phenomenology, like even Standard model, let's say, if you're trying to get Standard model from a type 2B string theory, or if you're trying to get inflation from a type 2B string theory, you're always going to get something. You're not going to get your potential. You're not going to get your desired potential. You need a separate uplifting term. Okay, you need to your V your V effectively requires some delta V term so that you go and get your required like de Sitter potential that you need, right? So what we in our model, and also it's a similar technique that was also used preceding to this model, which was it was a revisit of sorts. The name unfortunately eludes me, but it's a revisit of sorts to the brain anti-brain inflation, which was unfortunately mired by eta sensitivity, but after incorporating all these effects, it gave better results after about 20 years. So here, what we find is these moduli, moduli redefinitions that we tacked on to our moduli, they effectively act as our uplifting. So what we have is in our Kähler potential almost inherently inbuilt an uplifting, an uplifton. You don't have to add other terms that are maybe possibly not natural of sorts. They break naturalness of your model. You effectively get your uplifting immediately from your Kähler potential, which is not part of the models of most, which is not a part of most inflationary cosmology, string inflationary cosmology models, basically, from type 2b. Right? We use a very specific, all of these computations were done for a very generic Calabi-Yau, where we have 1 upon gamma terms and then lambda s term. Then we basically specified a kind of Calabi-Yau that we would like to use, where we have these prefactors. And for case 1, we found that for e-folds, because e-folds we have from 40 to, we have that 40 to 60 or 50 to 60, however you think of it, that kind of like bound wherein which you must have like effective inflation can take place. We found that for case 1 at n is equals to 60, we found these R and NS values, right? And for case 2, we found effectively at n is equals to 50 and around n is equals to and 50, we found such R and NS values as well. Both, this is a little tricky. This is a little bit beyond the 0.9743 kind of bound that we have, and a lot of fine tuning is required to get it down to this. But we found for case 2 a pretty good result. But case 1, if you could, I think with further playing around, you can also derive a similarly acceptable kind of NS value as well. Right. Anywho, so conclusions, finally, after droning on. So the interplay between string theory and cosmology really does bring forth like an exciting new path forward. String theory is a highly non-trivial, non-testable framework with the current collider technologies that we have. I don't know if even possibly in the next 50 years we would be able to gauge the kind of energies required to validate string theory. So these kinds of internal theoretical testings that we can do per se with standard model or inflation or let's say reheating and all of these, if we can explain from a top down a lot of these phenomena that exist in the universe today, then to physicists this is fantastic, right? So recently there are a lot of advances in connecting the two, reveal their potential in both kind of aspects. Because if you having a more robust UV controlled framework would give you, like inflation already gives you a lot of predictions in and of itself, but having inflation being derived from something that is UV complete, there's effectively more predictions to be made. What can we get effectively from the dynamics of early universe? And experimental efforts of the likes of primordial gravitational wave detections effectively poise themselves to kind of get of kind of validation experimentally as well, whether or not these models at all match with real life kind of techniques. So yeah, that's the end of my talk. Thank you very much, everybody.